There we go.
We'll deal with
That's
the results later, and hopefully get most of the class.
You have the desks.
Huh?
You have the desks.
I know, but I also have all the way up to here too. Yeah.
Yeah. Let me just look up in my screen.
All right.
Okay.
We can do stuff.
If you don't mind, I'm gonna go do work in the library.
I'd rather you were here to interact with me.
I know. It's just
A little weird, isn't it?
Yeah.
If you don't mind, you got another hour, right? If you don't mind.
Yeah.
All right. I would prefer, if everyone was here, but all right. So let's pull this guy down for a hot minute. No,
If only I.
no, we'll leave it there. It's hard to put. I didn't want a line across the screen. All right.
You're lucky I'm mentally incapable of paying attention to online classes. So I have to be. I can't leave.
Yeah. So, we are still working through our wave stuff. And as promised, we're going to talk about instruments today. New bitch off here. Instruments, is right. Instruments, all right. Come on. I dropped my chocolate on the other night there. Now I got a new bit of chop here. All right, instruments. So what happens with an instrument, such as a string instrument, like this guy right here? Well, what happens is that we have a method of excitation, whatever it is, such as this once was Razor. It is now a string vibrator, made by Conair. And if I plug it in, there's a little motor in here that'll start to vibrate the string. And if I hold on to this thing wrong, it'll make a horrendous noise. Fortunately, I figured that out last year, and we're not going to do that trick again. We're going to make just the right amount of noise. So, okay, so that means we have a wave that'll travel on down. All right, so we have a f of x. F of x is equal to our amplitude. We're going to send down a sine wave with the k, the x, the minus omega t. Goes on down the string. Okay. Well, what happens? When it gets to this point here, it's going to reflect back the way it came. Depending on the various odd conditions here. When it reflects back the other way, it may, if it's pinned down, it will invert and then go back. If it was allowed to move up and down, it will just go back the way it came. Okay, so now I got a g of x. I don't think it really matters if it inverts or not, what I'm about ready to do. So, given that this point is pinned down, I think it's going to reflect upside down, back the way it came. So we're going to get a minus a sine kx plus omega t. Okay. All right, so now I have two waves going down the string, which means they're going to interfere with each other in an active manner. So that means that my wave, my final wave, A, F, G, H, H of x, is going to be f of x plus g of x. And if you happen to know your trig relations, then looking at this, you'll realize this actually becomes 2a sine of kx sine of omega t. So what's going to happen here is that you're going to get this function, this here. It's going to wave up and down from one end to the other, and it's going to cycle between upright in one way to upside down. That means it's going to look like, if I were to draw it, rather than relying on my camera to resolve the string, it's going to look something like that. Alright, something like that. Okay? If I had a strobe light, which I don't think I do. I don't think I do have a strobe light. It is possible to make it freeze in air. Make it appear to freeze if it's moving. So this guy here, this guy says it's going to go from one side and back and forth. Between this side plus and that side minus, plus and minus. It'll keep going back and forth. This guy is the actual sine along the length of the string here. Okay, so that means that K has to have certain values, doesn't it? If K does not have certain values, I'm going to try what will happen. What the setup that's dictated is that this spot will always be 0, and that spot will always be 0, right? The only way h of x will exist is not 0 if x equals 0 and x equal L. Let's try it again. If h of x, h of 0 equal h of L equals 0. Right? Yeah. That's the best way to put it. So that means that this guy means that sine of K0 is 0, and sine of, let's try this here again, K0, always 0, and KL equals 0. Oh, well, ain't that convenient, right? Sine of 0 is, Andrew, you know what sine of 0 is?
Not with the pressure, no.
Is always 0.
Yeah.
So this is always satisfied. That's handy there that way. This guy, this is not always 0. Okay. Well, for values of sine, is there 0? There is this guy here at pi, and this guy here at 2 pi, and we keep going. Well, there's some more pi, so that means that k of k times L must be equal to n pi, like so. Okay, interesting. So that means that my k, my wave number, is always equal to n pi on L. All right, but that was inverse meters, and I need something, and that's inverse seconds. I need something to be, and the other day I said that omega on k, my angular velocity divided by my by my wave number must be my velocity. Oh, well, I got this guy for k, and my omega is 2 pi f, right? Yeah. Divided by this guy, n pi over L. So pi's cancel, and I get that my velocity must be equal to, L goes on top, we get 2 LF over N. Okay. So, we're almost there. I'm almost done with what I want to do here. Okay, so velocity is equal to 2LF on N. For a nice standing wave for this string instrument. Okay, well, velocity, what's velocity equal to? Turns out the velocity is also equal to the square root of linear density over tension, for instance. let's make sure that works out, right? So this is linear density. Mu is linear density of string, and T is the tension. So tension is a force, therefore it is in
Tension.
tension is a force, therefore it is in units of force are Isaac.
Second law of motion.
It's newtons. Plain old newtons. Linear density is the mass per unit length. Mass, that'll be in kilograms. Kilograms per meter. Let's make sure this works out right. Make sure I got it right. So I have a kilogram per meter, and a newton is a kilogram meter per second square. Should work out right. Oh, I might be upside down. Kilograms cancel each other, and so I have 1 over a meter square per second square, so this is a second square per meter square. Oop. So it means that the square root of this is not that. This is upside down, sorry. Tension goes here, mu goes there. Now it's upside down that. Let's fix that. Where's my red eraser? Here it is. Alright. Seems to be everyone's favorite eraser. Dang it! There you go, drop my chalk again. At least I didn't break everything like I did last time. Alright, try again. So this guy here, this is the square root of a tension is a newton, or a kilogram meter per second square, divided by the linear density, which is a kilogram per meter. Kilograms cancel each other. This inverse meter comes up on top, so multiply both sides, top and bottom, by meters. Those guys cancel. This is the square root of a meter square per second square, or a meter per second. Meter per second is that'd be a velocity. So this is correct here. Okay. So I would like to know the frequency. I'm going to rearrange this for frequency. So frequency, more often than not, you're going to find this given as frequency is it's going to be n over 2L square root of tension over linear density. Okay. So, okay. All right. Well, yeah, I got a string here. What I want to do with this string? I would like to measure the linear density of the string. Anything else I want to do with this? Actually, before we do that, we'll measure the linear density of the string in due course. Let me draw out a few possible solutions to what we can expect to find on said string. Okay. So, we can have a string that does, this is the lowest note that my string can support. This is called the fundamental. Using this guy, n is equal to, I believe, 0. 0, no, it has to be 1, right? Hold on. Okay, 0, no, that doesn't work. Must be 1. N must be 1, okay. So this is my fundamental. N is equal to 1. Alright, or something like that. Okay, well, let's run some numbers for this guy. Let's just say that for kicks, giggles, and squiggles of it all, 1 goes there, 2 goes there, L, let's just make it a meter. Square root of, let's just make it easy, 1 Newton per 1 kilogram per meter, goes like that. So now this is 1/2, and that'll be a hertz. So that'll be a half hertz. That's obviously not what we're looking for, but what I want to know is, what relationship is it to the next guy? Well, now I replace my n with, instead of 1, I'm gonna replace it with 2, okay? So then we got 2 over 2, put in all the same other numbers for 1 meter, 1 kilogram per meter. Make that 1. Oh, so this is 1 hertz. Okay. So then I do it again, and so now I got 3 here. So I put 2 here instead, right? 2, 3, so next one will be 3 hertz. Right? No, 3 halves hertz, sorry. So as it goes down. Okay, so then this guy. This is, alright, so this is the fundamental. Let's see here, overtones, harmonics. This is the fundamental, the first harmonic, let's go right, or the 0th overtone. Alright, well, so then this guy here, this would be, well, it's not fundamental anymore because that's only one value can do that. This would be n equals 2. This is the second harmonic. And the first overtone. Okay. And according to these guys, this frequency, this F2 is twice F1. This is just our F1. Alright. So then we go to our next one. We can also support that guy. Alright, so this will be n equals 3. This is the third harmonic. And the second overtone. And this F3, is equal to what? Now this will be, well, this will be 3 times F1. But it'll also be 3 halves. Oops. This will be 3 halves F2. Okay. Alright, next one. Looks something like that. Alright, so this will be n equals 4. This will be the fourth harmonic. The third overtone. And this F4 will be equal to 4 times F1, or 4/3 F2. No, not 2, F3. There we go. Okay. Alright. Interesting. Okay. I'm about ready to go down the line of just intonation.
Is this why decibels are increasingly higher?
No.
No?
No, this is why when you look at a spectrum plot of sound, the frequency is usually given is usually on a log plot. Now this is so this is about pitch. Decibels is about how loud it is, about volume and amplitude. So it's somewhere in the neighborhood, but it's not the same. So this guy, so going from here to here, this is an octave. Everybody agrees that doubling the pitch, doubling the frequency, will get you an octave. 3 halves. This is in what is known as in just intonation. This is in just intonation. At 3 halves is a perfect fifth. Four thirds, this guy here, in just intonation. That is, that's a major third. Oops. Major third. And we go one more. I don't know if I want to draw one more, but I'm gonna go ahead and do all of the math. So that'll be n equals 5. That'll be the 5th harmonic. And the 4th overtone. As if that wasn't obvious enough. And so we got F5 will be 5 times F1, but it's also 5 quarters of F4. And this interval here, third, that's a minor third. Just intonation. This is a minor third. Based off these intervals, you can construct the rest of the intervals. If you want to go the other direction, this is also, I believe this is a major 5th? No. That's a major 6th going the other way, so 4/5 is a major 6th. This would be a minor 6th going 3/4, and then 2/3 would be a perfect 4th? Yeah, be perfect 4th. And then an octave going back this way, well, it's still an octave. If you go back to yourself, this is called unison here. Unison. And everybody agrees on unison and octave. So I've noted that these are just intonations. Why? Because just intonation, for a long time, just intonation was the way we did all of our tuning scales. And so there was so that was the standard, which means that depending upon your key, so if you decide that this was C, this guy here was C, and then you built off the rest of your octave built off of that. You get some notes. Ta-da! Notes done. Well. Then you decide that, well, I don't want my root to be C anymore, I want it to be A. Well, your A is defined in this scale here, and your just intonation here. So when you switch over to A, that means that all of the intervals in A don't match up with the intervals in C anymore, and that'll color your the emotions and flavors, the sounds and intervals of your A being different from your intervals in C. Well, there was not a whole lot of agreement, so there's, in an effort to make standardization a thing and make pianos work nicer, we got 12/10. What is it called? Well, it's shorthand, it's 12/10. It's called 12. Is it 12 tone? Equal temperament. Yeah, 12 tone. Yeah, 12 tone equal temperament. Which means that this the minor second means that a ratio became a ratio of 12 to the 1/12, rather than these ratios. Sorry, these ratios right here. And so and instead of, so let's hear so the octave still becomes an octave in that situation. This guy here, right? The perfect 5th would be it's not 6, I think it's 7. So in 12/10, 12 T E T 12/10. I think this guy here, he becomes 2 to the 7/12, which is something entirely different. Let's see if I got that right. 2 to the 7/12. Should be in the neighborhood of 3 halves. It is, I got it. Success. So, instead of a ratio of 3 halves here, you get that guy, which is 1.4983 instead of this guy here, which is 1.5. And some people can hear the difference. And I don't think I'm one of them. But there's definitely, when you get the whole collection of all your instruments changing out from just intonation to 12 tone to 12 head, it is noticeable as a whole. And I believe they'll in fact color each key differently from one to the next, which is a whole lot of music theory that I'm like, it's a thing. But that's where music theory goes, right? Anyhow, so there's strings. That's what these guys are. That's what the guy got. That's what that guy. That's what that guy is. You can also do. There's a variety of other ways you can do this trick here. So we have these guys here. We can also do fundamental. We can also put wind into pipes, and those work out. Those will do a similar kind of thing. I don't know. The book is not interested in pipes. The book is interested in strings. But I'm going to go ahead and draw some pipe ideas here. So I believe flutes look like. Am I spell right? Flutes and similar instruments are basically pipes that are open on both ends. In that case, you get the lowest note looks something like that. And of course, you can put in more harmonics into that guy, and it'll do that number. So you have so instead of having nodes on the ends, you now have antinodes on the ends. Pipe organs will also do this. Think they'll do it? No, they don't do that trick. Pipe organs will do this number. So this is a pipe organ here. Pipe organ. And also saxophones and like a good chunk of your brass instruments will also look like something like this. And so the lowest note these guys will make look something like this here. And the next one up will look something like that. It's possible, because your excitation is here, you got the air coming out there at that point. You can also, for a pipe organ, you can also cap it if you wanted to. In which case, that guy goes there, and we're back to a string. We're back to the fundamental looking thing from strings. Flutes, pipe organs, yeah. Enough of that. Anyways, so 37. We got lots of time. All right, this guy. Assuming everything goes well, I would like to know what is the linear density of this string. Ready? Yeah. So, okay. My string shaker here can put out precisely one frequency, 120 hertz. Humans here in the interval of 20 to 20,000 hertz, which means this is audible. Also there's also the transformers, such as the ones that are in these fluorescent lights here. They also vibrate with the AC electricity coming in, so they should make a 60 hertz hum. We can speak up. All right, let's see if my power cord will go far enough. All right. on. Come on, around. Around we go. Oh, no, that's the far way. That's just good, because I want this power cord up here where I can turn it off. Why are we not on?
Is it not on button on this thing? How very strange. You may need to get some power from somewhere else.
Oh, it is on. Power should is on. Why are you not on? So we can get out of here without making a whole mess of everything. Come on. There we go. That's a lot more noise than I should like. I thought I learned my lesson. Some told me I did. That's sure face.
It's a very fast vibrator connected to a steel rod. It's
Yeah.
gonna make noise.
Now, there's a way to make it make less noise. And that was not it. Come here. Alright. See? Less noise. Still more noise than I should like, but it's not nearly as loud. Where are my multi-tools over here? Alright. Oh, good. Everything's still working in its right spot. Okay. So, first thing I need. Is a relationship between the tension I put in my string and is that a good way to put it? Yeah, that's a good way to do it. Maybe? Hold on. I'm gonna take this guy here. I'm gonna get mu by itself. So I now have F squared is equal to N squared over 4L squared, tension over mu. Get this guy by itself, throw it over here, throw that over there. We get that mu is equal to N squared tension over over 4L squared F squared. Okay. I thought this was linear. Oh well. Alright, so I am going to alter my tension. F stays the same, length stays the same. N will change? No, hold on. This is the way I want to go. We'll make it work. This will work for us. Okay. Alright, well, before we do that, I know what F is. F is always 120 hertz. I know this because I asked my phone, that phone there, what the frequency was, and it said that. It already said that for me, so I was like, that's nice. L, I know that. Tension will measure over there. Mu is what we're looking for. N and T, yeah. So I need the L. L, we need that too. Alright, L. So, today we have a 2-meter stick. And we're glad to have it. Alright, I hope it's not more than 4 meters. That'd be rather quite unhandy. That goes there. That goes there. Alright. Yeah. Oh yeah, just barely. Alright, hey Andrew, could you do me a favor and tell me how long the string is over there? Let me double check, make sure I got the bang. Make sure I got this in the right spot. Alright, that guy goes there. Okay, then you're staring at the spot. And it goes right about there.
Yes, stair method. One of the most
Yeah, I know, right?
accurate.
I know, right? That's exactly.
Where do you want me? Right here?
Yeah, right there.
The 7.
Is it all?
17 millimeters.
17 centimeters?
Centimeters back.
Okay. I think that probably
So
goes to 18. So that's 4 meters less 18.
800 or that's 400 minus 17.
Yeah. I'm gonna say that that post is pushing back with a centimeter. So I'm gonna say 18.
83.
So 400 minus 18 is
383.
380. I'm gonna go 382.
You would, wouldn't you? You like that?
I'm trying to be consistent with what I'm feeling that meter is rather quite unhandy. Alright, 380, 380.
Then again, the pole meters were placed manually and not measured.
Yeah, 382 centimeters. Alright, we have been, we are, shall we say, lucky on this.
Supposed to do that?
Was that?
Isn't it supposed to do that?
Well, what I'm trying to do is I'm trying to maximize the amplitude of the vibration here, and it's not quite there.
It's 7.
It's yeah. That's so I'm aiming for 7. Yeah. 1, 2, 3, 4, 5, 5, 6, 7. Yeah. So we got 7 here, but it's not quite maximized. A little bit more.
Oh, it's the weight detention?
Close enough. That is 1 kilo and 10 grams. So that's alright. So N equals 7. Tension is given by mg, and our mass here. So let's put that mg in there. N squared mg over 4L squared F squared. So our m here is, I'll take a few of these here. N equals 7, and m is 1.010 kilograms. Alright. So, if I reduce the tension here, then my N should drop. More than that. So, good. more. Which one? A little more. Yes. We'll take that. 6? Should be 6. 1, 2, 3, 4, 5, 6. Yes. Alright, oh, these are notes then, aren't they? So 6, 7 notes, and let's see here. Add 1. So that's not right. So this guy here, this was 7 notes, which means n equals 8. This one, that's 6 notes, so this is 7. And that was, what we got here? 40, 50, that's 90, it's 10 grams down. That's 20 grams down from that one, so that's 0.980 kilos. This much. A little more. Just a little more. No. This little more. Oh. Oh, let's go for it. Let's just go for lots less. What? I wonder what's going on here. Huh. Well,
I had like 8 or 9 there.
yeah, that's some weird stuff that's going on there, if you ask me.
I think, is it the clamp? I don't
Yeah, because as a, so, hold on, did I get my, hold on. Mu is constant. Why did we do that? F is constant in, inverse, F n goes, wait, what? Really? Hold on. Plus 1 is 7. Plus 1 is 7, okay. Get there. And 2 grams more. 1, 2, 3, 4, 5, 6. What?
That's
1, 2, 3, 4, 5.
7, the one next to your finger.
That's not that. I'm carrying on ones between here and there. So ignoring this one.
No, I know, but
Okay, so this one here, this is 1, 2, 3, 4, 5, 6. Alright?
oh, you mean we're counting over teams, not harmonic.
1, 2, 3, 4, 5, 6. Plus 1 is 7. So that's for this guy here.
And 70.
And then if I take off 20 grams, this goes here. This comes off. And well, 50. And 40 more. One, two, three, 4, 5, 6. Huh. Well, at least it's reproducible. Well, that's weird. Plus 1 more is 7. Huh. I wonder. I bet I got 2 frequencies going on here. And that makes it hurt. So, 2 frequencies. If I have 2 frequencies, I can support either of them, and I suspect that's what's going on here. But I did not see that last year, so I'm mildly confused. That's interesting.
I blame the clamp.
Possible. I wouldn't blame the clamp itself. But it might be that there's a big, huge mass on it because I didn't do it this way last year. That's weird. Anyhow. Huh. Alright. Okay. So.
It's like the sound of a heater, but there's no heat. And instead I'm freezing.
Was that?
It's like the sound of a heater, but there's no heat.
Yeah.
And I'm freezing.
Oh. No. Anyhow. Let's go ahead and grab these guys and see if we can't make a prediction for a different mass instead of going, where is it? So, I'm gonna take these guys, shove them into here, and find out what mu we got, and then we'll try to find out what n we can get. So, mu is equal to n squared. The mass, we'll just do that there as is. Mass in, try again. N is this guy, squared is 49. Mass is, we'll put that in later. Gravity is 9.8 meters per second squared. Divided by 4. My L is 3.82 meters. And my frequency is 120. Don't forget square. 120 inverse seconds squared. Alright, so that number is that is a mass that's in kilograms. That is going to be in kilograms, okay? So that means that the rest of this will be in inverse meters, okay? 49 times 9.8 divided by 4 times 3.82 squared times 120 squared. So this is 0.0005 713. This here. We'll put the mass over here, and this will be in inverse meters. Okay. So we're going to take this guy and we're going to multiply. Make sure you got everything there, right? Multiply by mass here. So that's 1 by, it'll be 1.01. That'll give us, for this guy here, this guy says 5.77 grams per meter, like one here at 0.98. Figure that out, 0.98. Says it is 5 point, right? Well, multiply by 1,000. 1,000 to say. Yep. 0.5 there. 560. 560 grams per meter. So it's about half a gram per meter. That sounds like a string to me. We have 15 minutes yet. So let's see if we can't find another n using these guys here. So let's go with, if we go n equals 1, what do we get? I don't know. N equals 1. I need to solve this guy for, I need the mass here. So that'll be 4L squared F squared mu over N squared G. Okay, so that'll be 4 times 382, no, 0.82 squared times 120 squared times 0.5, 0.000577, 577. Where do you go? Divided by 9.8. Okay. So this guy says it's going to be 4.95 kilos to get that far down. Okay. So I guess that means we need to, if we wanted to go, so we're going to need about 5 kilos to make it to the first, to the fundamental, to make it vibrate. That is a lot of weight. I don't feel like putting 5 kilos on there. Let's go with, let's try n equals 6. You want to do 6? That means more mass. I like that idea, more mass. Let's do that. N equals 6 is equal, will get us over here. Insert there. No, there's no right. 6 squared is 36 times 9.8. Oh boy. That's a heck of nothing. Really? If I go 49. Oh. It's even worse than I thought it was. Apparently I can't convert my units right. Tell that. There we go. So, if I did my units right, this is actually not that. It's actually 49 kilos. 49 and a half kilos. That's like half of me, I think. Yeah, I think that's about half of me. No, we're not doing that. That sounds terrible. Let's try going for 6. 6 requires 1.3. I didn't bring any grams over here, so we're gonna try 1.40 kilos. Let's try that. Let's try 1.4 kilos to see what we see. Switch this over there. Alright. Let's see if we can make predictions with what we have. 1.4. Alright. These guys come. Alright, 4-0. Here's 1. Alright. 4-0. 1.1. 1.2. 1.3. 1.4. Oh! Actually, this is gonna be over.
Hey, it worked.
It's actually 137 is what it actually is. Right? Yeah, 1.37. So it's actually over by 30 grams. I got that resolution.
It literally worked.
Is that?
It worked.
Yeah, well, I got, get all the way down there. Alright, so There's 50. There's, no, that's not Stumpy. This guy. Ta-da! That's working. So, what we got going on here? 1, 2, 3, 4, 5. The math works. How about that? So that is indeed, that does apply. We're going to need about 49.5 kilos to get to the fundamental, to make this vibrate, to make 120 hertz the fundamental of this string. That's a lot of weight. Like I said, I think that's about half a me. And so we're not going to do that. But, anyways, so we are going to, I'm going to yammer a little bit more about some musical instruments. Because I have a little more time. I got 2 minutes. Okay, so why is this interesting? Why is this useful to us? Other than musical instruments. Well, this is actually the start of quantum mechanics. So each one of these is a single vibration along a 1D axis. We can constrain electrons to exist in a one-dimensional space. And they also vibrate kind of like this, but with more complicated math. If you had a symbol, so these guys sound pretty good to us because H string will produce these overtones that match nicely with all the ones that have come before. But the math for symbols is a little different. They can come in, if the fundamental of a symbol is the whole disk coming in and out. But you can cut it in half, and you get plus here and minus there, so this guy comes out and this guy goes in. We can also divide it radially, like this, so that when this guy comes out, the outer ring goes in. We can take a symbol. And so these are not the same frequency. And it's not a pretty relationship like one of those. And we can also combine them so that, like so that this guy goes in, this guy comes out, this is plus, this is minus, and it does like that. And so we can divide the symbol up various odd ways as necessary. So the fundamental symbol looks like that. But none of these frequencies are nice round ratios like these guys are, which is why when you strike a cymbal or a drum, they crash, they make noise, but they don't make pleasant noise unless you design it just so. See the steel drums. Steel drums sound amazing. But most drums are inharmonic. They just make a sound. And so what you do to make those make music is you play the beats in these ratios. So the intervals on the drums are these nice ratios here, right? And so the intervals at which you play those drums is not an audible frequency, it's an inaudible frequency. But the ratios at which you pick instruments off the drum kit are still these ratios. Which means just because your instrument is inharmonic and making noise doesn't mean these still don't apply to you. They still apply. Anyways, but quantum mechanically, you can put your electron in 1D space and get the strings. You can put your electrons in a 2D space where if it's in a circle, you get these guys. It is possible to put them into a square. In which case you get to take these guys and multiply them into a square. So you get things that look like, you can divide it plus and minus, or plus here, minus there. You can do stuff like that. And then if you get really fancy, when you go to 3-dimensional space, You can get these things that look like those guys rotated and also coming in and out as a whole. Or you can slice it up like those guys, and yeah. So there's lots of ways that are, these things can come back to us. Time is that. So I think that is a perfectly good spot to stop. I'll probably yammer on some more about these guys on Wednesday. Is it still rolling?
Yes. You
You
want
can
to
hit
turn on?
stop on it.